Dear students, in this lecture we will discuss about the oxidation state of lanthanides and their compounds in solution form and in solid form of the compounds. What are the general properties of lanthanides? Dear students, as you know that the valence shell electronic configuration decide the properties of elements. In lanthanides, the valence shell remains same. The electrons are being filled in third last 4f subshell. Due to the reason that valence shell electronic shell remains same, so all the lanthanide elements have very close physical properties as well as the chemical properties. Both are almost closely related, close resemblance, nearly similar. Why? Because the valence shell remains same. Now we will discuss the oxidation states of lanthanide cations. Tripositive lanthanide cations, it has been noted that all lanthanides possess +3 oxidation state in solution as well as in their insoluble compounds. Few lanthanides can possess +2 and +4 oxidation states either in solution form or in their compounds, which may be in solid states. The table clearly shows the oxidation state of lanthanides. Why the tripositive species are more stable? Scientists explain that oxidation state depend on two values. What are these values? The magnitude of the ionization energy for the removal of electron and the interaction between water molecules and the gaseous ions which have been added in water. It means two terms must be considered to explain the tripositive species stability. These two terms are ionization energy and hydration energy. The ionization energy is a positive quantity, while that of hydration energy is the interaction between the poles of water molecule with ions, and it has a negative value. Greater the hydration energy, less the ionization energy. For the lower oxidation state of lanthanides, the lanthanide which fulfill the following conditions, which I have just explained, mentioned here, then the species with tripositive ion will be more stable as compared to the species having other oxidation states such as +2 and +4. But there are certain exceptions in this general rule, that is the cerium +4 and europium +2. However, all these dipositive or tetrapositive ions, when added in water, when tetrapositive ions, positive species, are added in water, they revert to the tripositive oxygen state. But there is also certain exceptions. The exceptions are cerium +4 and europium +2. These never revert. All other lanthanide as cerium +2 type species and europium +2 type species, other than these two, revert to the tripositive species. Scientists concluded it means that tripositive ions are more stable as compared to di and tetrapositive species in aqueous solution. Simply we summarize these concepts that low the ionization energy, high the hydration energy for a species having a positive charge is more stable as compared to the other species having +2 and +4 oxidation states. There are all lanthanides with +4 and +2 oxygen state revert back to tripositive ions in solutions except cerium and europium. This leads to the conclusion that tripositive species are more stable as compared to the di and tetrapositive species in aqueous solution. Lattice energy of solids can also explain the stability of tripositive species of lanthanides. To understand this one, two terms must be kept in mind. The first term is the ionization energy and the second term is the lattice energy or crystal energy. The ionization energy is positive quantity and the lattice energy is due to the interaction between the oppositely charged ions, which interact with each other to form the lattice. It is a negative value. It means low the ionization energy, removal of electron from the valence shell of a species, and more the negative value of lattice energy. When these two parameters combine, then the species will become more stable. These two values favor the tripositive species as compared to di and tetrapositive species. So consequently, we can say that tripositive lanthanide ions are more stable in solid compounds. Stability of various oxidation states. The first discussion point is whether the electronic configuration can be used to correlate with the stability of the oxidation states. Yes, the concept of electronic configuration can be used. Let us think that three terms must be prominent in deciding the stability of oxidation state and electronic configuration relationship. The first one is empty 4F, half-filled 4F, and completely filled 4F. It means the completely filled 4F orbitals are highly stable, half-filled are stable, and similarly the empty, if produced 4F0, it is also more stable, and these three conditions will give the stability to the oxidation states of the lanthanide species. For example, the formation of cerium +4, lanthanum +3, thorium +4, europium +2, gadolinium +3, terbium, lutetium. Let us check what is their electronic configuration. Cerium +4, lanthanum +3, 4F0, highly stable configuration is obtained. It means such type of, and next see the next, thorium, europium, 4F7, half-filled, highly stable, and next terbium, lutetium, 4F14, highly stable. So when after the loss of electron, after the formation of species, more stable configuration is attained, then the species have more stable oxidation states. It is, however, difficult to explain the stability of oxidation state of cations other than +3 and +4 because they have 4F0, 4F7, 4F14, which are stable, but such species have no 4F0, 4F7, 4F14, means the other species have partially filled F subshell which have less stability, but the oxidation state are stable. Scientists explains that only the electronic configuration cannot be used to explain all the oxidation state of lanthanides and their stability, other parameters must be considered. The other parameter which must be considered are thermodynamic concept and kinetic concept. Thermodynamics and kinetics. Knowledge of these two must be used to explain the stability of other oxidation states of lanthanides which have partially filled F subshell. The detail of thermodynamic and kinetic concept is not necessary at this level. Now, the oxidation state can be related to the electrode potential values. The electrode potential means the tendency of a species to give or gain electron. The species which give electron is self-oxidized and it reduces others. So it is called reducing agent. And the species which is self-reduced, which get reduced itself, acts as oxidizing agent. It means the tendency to reduce and tendency to oxidize can also be used to explain the stability of the oxidation state of lanthanides. The +2 oxidation stability order of europium, terbium, samarium, thorium, etc. are in the order. Check the order. Europium, the maximum stability of +2 oxidation state, and neodymium is the least. Lanthanide solids do not contain the ion because they are present in solid state. The +4 oxidation state of cerium, terbium, etc. is in the order. The order is given. Cerium has maximum stability of +4 oxidation state. Dysprosium has the minimum. The ease of formation of various oxidation state solution is indicated by the value of their standard electrode potentials, that is E0. E0 standard electrode potentials are measured at 25 degrees Celsius or 298 Kelvin with reference to standard hydrogen electrode. Now check the following couples. Lanthanide 0 to lanthanide +3, 3 electrons have been lost. Lanthanide +2 change into lanthanide +3, 1 electron has been lost. Lanthanide +3 has been changed into lanthanide +4, 1 electron is lost for 1 molar perchloric acid at 25 degrees Celsius. We observed that. What we observed that? Check these points. The high positive value of oxidation electrode potentials for the couple lanthanide 0 to lanthanide, Ln is a symbol for all lanthanides. Lanthanide 0 to lanthanide +3, 3 electron indicate the elemental lanthanide are powerful reducing agents. Those species which are powerful reducing agents can reduce other and get itself oxidized. It means the conversion of lanthanide 0 to lanthanide +3 is easy. And now listen to this statement. The gradual decrease in the value of E0 indicates very slight decrease in chemical activity from one element to the next one. The next concept is the enhanced stability, increased stability is associated with the same concept which has been discussed in previous slides. Half-filled, empty, and completely filled orbitals. If such type of electronic configuration is attained after the loss of electron, then the species are more stable. Thus, cerium +4 that contains the 4F0 is much less readily reduced to the tri-positive ion. It means it is difficult to reduce the cerium +4 to +3 because it has the configuration that is highly stable configuration after the loss of 4 electron, that is 4F0. Cerium +3 that is 4F1. Promethium plus 4F1. It means if a species has unstable electronic configuration in 4f orbital, that is partially filled electronic configuration partially filled orbital, such species are the weakest reducing agents, and the species which has weakest reducing agents must be highest oxidizing agents. And the third one is the value of E naught for couples lengthenide 0 to lengthenide plus 3 decrease with the increase of atomic number. As the atomic number of lengthenide increase, the E naught value, electrode potential values will decrease. Now, check the chemistry of plus 2 oxidation state. Scientists explain this oxidation state as anomalous oxidation state, incorrect oxidation state. Away from routine value is the oxidation state plus 2. Scientists have divided the lanthanides which have shown the plus 2 oxidation state in their compounds or in solution form are divided into two categories. The first category contains these three elements: samarium, europium, terbium. The dye-positive ion of these lanthanides exists in solution. The standard reduction potential values. What are the reduction potential values? The tendency to get oxidized or reduced can be expressed in standard reduction potential values. If a species has negative standard reduction value, reduction potential value is strong reducing agent and self-oxidize. If you think about electrochemical series, the elements present at the top of the electrochemical series are powerful reducing agents. Check the electrode standard reduction potential values of samarium, europium, terbium: minus 1.55, minus 0.43 volts, and 1.14 volts. These values indicate that the minus value shows that these are the strong reducing agents, and their reducing strength can be given as on the basis of value of standard reduction potential. The first one is samarium, the second one is yttrium, and third one is europium. Samarium plus 2, yttrium plus 2, terbium plus 2 ions terbium plus 2 ions are rapidly oxidized by H3O plus ions, while europium plus 2 ion is fairly stable and is only slowly oxidized by water containing acids, that is H3O plus ion. Check the reaction. You can write terbium instead of samarium also, and the same type of reaction occur. All these cation is rapidly oxidized in the presence of oxygen, which becomes self-oxidized, is called reducing agent. We know that. Check the reaction. Now we will discuss the reaction of lanthanides with water, in which lanthanide ions act as reducing agents. It means if something reduce water, then water give hydrogen gas. The compound of samarium, europium, terbium, which are insoluble in water, not oxidized by water, while hydrated water soluble compounds of samarium, terbium are oxidized by water. These can be oxidized. 2 plus 3 oxidation states. Hydrated water soluble compounds of europium are more stable. Other are less stable, but europium are more stable. The category B, cerium, neodymium, thulium. The compounds having these elements in plus 2 oxidants are known as only in their halides. The halides of these elements, of these lanthanides, have the oxidation state plus 2. but these are immediately oxidized with air to lanthanide plus 3. Plus 2 to plus 3. Of the divalent compound of lanthanides, European plus 2 ions are more stable. Think about the configuration after the loss of plus 2 electrons. The compound of lanthanide plus 2 ion are not stable in solution. In solution, they get oxidized by water into lanthanide plus 3 ions. But when water oxidizes lanthanide ions to plus 3, then water get reduced into hydrogen. Now, check the chemistry of plus 4 oxidation state. It means few lanthanide exhibit the plus 4 oxidation state in their compounds, especially the double salts. This oxidation state is also an anomalous oxidation state. It is not commonly occurring. Away from the routine oxidation state values, double salts as given cerium nitrate, dot ammonium nitrate have also been prepared. The oxidation standard reduction potentials of cerium and promethium have been given here. The reaction shows the reduction occurs from plus 4 to plus 3. The standard reduction potential values are positive. If a species has standard reduction potential value with positive sign, that shows the species is oxidizing agent. Their values show that cerium 4 and promethium 4 are strong oxidizing agents. Cerium sulfate is generally used in volumetric analysis. Cerium plus 2 ion will readily reduce to cerium plus 3. It means cerium plus 2 has get 1 electron to change into cerium plus 3. The species which gets electron is self-reduced but oxidizes others. It means these species are oxidizing agents. The tetravalent ions of cerium are stable in solid state as well in solution. Promethium, etc. are stable only in solution. Chemistry of plus 3 oxidation states. We have discussed in previous slides that all known lanthanides almost show the plus 3 oxidation state, and these plus 3 cation, when combined with the anions, then the compounds are produced. And when compounds are produced, then we say that the plus 3 oxidation state of lanthanide is stable in their compounds. Their compounds are stable in solid as well as in solution state. Compounds of lanthanide plus 3 with anions such as OH negative, carbonate, sulfate, etc. decompose on heating, giving first the basic salt, the salt which contains the OH ions. Salt containing OH ion is called basic salt, and the salt containing unneutralized H plus ion are called acidic salts. And when the first basic salt went heating further, then finally oxides of lanthanide are produced. Compounds of lanthanide cations with the anion, chloride, bromide, iodide, nitrate, acetate, etc. are generally soluble in water, while that of fluoride, OH are insoluble because the lanthanide fluorides, hydroxides, oxides, oxalates have very high lattice energy and low hydration energy, so they are insoluble in water. Thank you very much.